way to fix that. So it's fragile and hard to extend, especially for bigger projects. So this is where codes come along. Codes are fix precisely these issues because we are, instead of translating immediately from type to its representation in star, we're actually going to be talking about a code which the representations will be defined by induction over. So we are adding some structure to the representation which allows us to either make more assumptions or write functions by induction on this representation instead of on the actual star type itself. Now in Haskell, types come in sums of products form, which is a normal form for types, and it's very handy to have those. So we are going to be borrowing a lot from generics SOP, which was presented on the True Sums of Products paper a couple years ago. Very cool library, and in fact, we're now going to be talking about the codes that define our data types, and then we're going to later on map these codes back to star, which will give us the values that we need to work on top of. But nevertheless, our binary tree has two constructors. So you have two elements on the outer list. The first constructor has something of type A, so it's an A here. And the fourth constructor has two values of type bin A, which show up here. So we are going to be reflecting the sums of products structure into a nested list of stars, which contains the type there. Now, mapping this back to star might be a little bit tricky, but if we digest this, we actually see it's quite simple. So the NS stands for an NRE sum, which is what we're going to be using to select which constructor was used. So the choice of here and there basically simulates the choice of constructor you had, and an NP is going to be used to map all of the fields of the constructor back to star themselves, and we're going to be mapping them back to star with the identity functor. So this is the representation, which has kind list of star to star. An example perhaps makes it much more clear. Let's say that we want to write the constructors of our binary tree type together already into the. Oh, there's a big typo here. There should be bin. There. So the leaf constructor would be the first constructor, so it's a here, and then we actually have to provide an NRE product indexed by the list with one type. So there's only one cons, and we can actually provide its argument there. And the bin constructor, which is the second one, receives two trees, or two bins. Should have that types in it. But it's the second constructor nevertheless. So there's there here, and then we actually have to provide a NRE product indexed by list with two bins inside, and we can do that with two cons. So it follows quite naturally from that. The advantage of that is that we can now define a bunch of combinators, and this is what I mean by combinators, is that we can define some functions that behave in a homogeneous fashion in all NPs or NSs, and hence will behave in a predictable fashion with all data types. And these are actually very easy to define. So for instance, we could eliminate a product back to a list by applying a function to each element of this product. Or we could eliminate a sum back to a single star, type of kind star, by applying a function to whatever constructor was chosen there. And this would allow us to define our generic size function now as a one-liner and just one type class. So we are already much better than before, where we had a bunch of type classes that could actually break depending on certain choices of wrong representations. Now we actually have just one type class that says, well, some types can have a size function, and the way we implement this is quite simple as well. We start by translating something to its generic representation. We then eliminate the constructor by applying something that applies size to every field of the constructor. So this is what this says. And then we sum everything up and we add one. So that is the size of a tree written in a generic fashion using a combinator-based approach. Note that not only we still don't have explicit recursion here, so recursion is still implicit in this approach, and which is why we actually need to make sure that every field can actually have a size, in the sense that it needs to have an instance of size, which is this class here. Otherwise, we can't call this size. So, still somewhat cumbersome to write, especially for bigger examples, these constraints go very large, and we don't want to have that. And this can be fixed by adding explicit recursion. And this is exactly the sweet spot in design that we have reached with our Mr. Sub library. So the first step is to augment the language of codes. So here, just like before, we added some structure to represent sums of products. Now we're going to add yet more structure to also represent whether these fields are induction or not. And we do that by adding a atom data type, which is then promoted to a kind. So these things are data types, and this is a kind. We interpret atoms by, well, either it is a whatever type variable is there, so be representing a recursive position. We use I here just to be homogeneous with the previous choices, but this is not the identity functor. Or you can have a choice of opaque types, which are basically the Haskell values that are going to be present in your tree. You could have as many of them as you want, and if I have time, I can show you how you parameterize over those. But for the sake of the argument, let's consider just integers. Now your representation, your codes actually are of kinds, list of atoms, and you need to receive some type to plug into every place where there's an I atom here. And you define the representation just like we did before, with an NR sum of an NR product of an interpretation for atoms. And this is able to handle types with a single recursive type. So we call this regular type. Now, if we actually want to represent neutrally recursive types, we can quite easily do that, and it's quite a small leap from here actually. Once you realize that, well, instead of one recursive position, I have n recursive positions, and instead of giving a list of recursive positions, I could give a functor from that to start, which tells me which position I am at. And all of a sudden, that's it. We have our interpretation for atoms receive a functor which, given a number, tells us which recursive type is on that index of the family. So an I3 would mean the fourth, we start at 0, so the fourth recursive type in the family. And our representation also receives this functor, and we can tie this knot like this. And to see this at work, let's take a look at an example. The classical example are rows trees. Although these are just a nested data type, they can also be written as a mutually recursive type, so let's pretend they are a mutually recursive type. For the sake of the argument, I'm also going to be applying them to int, because they have to be fully applied for this approach to work. Nevertheless, we say that the family is a rows tree and a forest. The point of this being that there is no recursion that goes outside of these two types. So all of the recursion is constrained within the types of this list. And we would then define the codes for each type as being what you would more or less expect. We would say that the code for a rows tree would be a constant integer, which would be the first thing here, applied to int, of course, and a recursive type, which is the second recursive type of the family. The code for the forest, on the other hand, would be either the empty list, which is the empty forest, or a cont, which has the first recursive type, the first type of the family, and the second type of the family. Hence, the codes for the family would be, of course, in the same order as here, otherwise this all breaks. And we will then package in a type class. Instead of calling it generic, we call it family. And this is all fun and games, but unfortunately it's not like this. Okay. So, to summarize, we have to define a family, which is a list of star. Have to define the codes for this family, which are list of atoms. Each type is a sum of product, and then we have a list of those. And then we define a lookup function, which basically tabulates this list and gives us that not to star functor. And we would say, all right, the representation of the ith type of the family is look up the ith code, represent it, and on the recursive positions, just go find the nth type of the family. But lookup as a type family can't be partially applied. This doesn't work. So what we do instead is we wrap it in a GADT. And all of a sudden you can partially apply it, and it works like a charm. So we actually have our family of isomorphisms, and in this case we have one for each type in the family, and we can then package it up and represent our mutually recursive families. It's worth mentioning that only well-formed representations are accepted, so you might be wondering why didn't you use finite types in your Atom language, and that's because this is really a pain to work with in Agda, and not to mention in Haskell. So we decided to take a little bit more permissive approach, which might seem too permissive, but it's not in fact, because had you written the codes for rows tree to reference the 43rd recursive type in the family, the instance will be impossible to write because the lookup type family throws a type error, and this means that malformed codes imply uninhabitable representations, so we are all fine. And this is in fact the key design aspect into making this library easy to use, or at least as easy as possible. All of these errors are covered compile time, which is what we want. We also have list fixed points for our approach. In fact, we can say, all right, the fixed point, which represents the whole tree, consists of looking up the ith code in the code, and on the recursive positions, just going up by the fixed point again. And we can define the deep conversion quite naturally by saying convert the first layer, and then map the deep conversion on each recursive position. And we happily win catamorphisms, anamorphisms, all the attribute grammar stuff, and there's no need to carry any constraints around. In fact, our gsize function now is written as a neat one-liner like this. It's a deep conversion and a catamorphism applied to it. So we have reduced, and this actually works for any mutually recursive family. Since I'm running out of time, we support custom opaque types. You can check out the paper how they work. So yeah, it is another feature from our library. So we parameterizable by the choice of opaque types you want. We also support zipper for mutually recursive families, which is a great self-validity test per se. If you write a generic programming library, it better support zippers, I guess. We also support automatic and family generation with template Haskell, and we support metadata just like generic SOP does. Was a very interesting project for a bunch of reasons. First, we found 2 bugs in GHC, one of which has been closed, the second which has not been closed, and the second is a memory leak. So everybody that's familiar with the exhaustiveness checker, please look at this. Thank you. It is very handy to work with deep representations, and this is really the lesson. So for working with arbitrary ASTs, we learned that although there might be a performance drawback from translating everything to its deep representation, it's much easier to write generic functionality instead of carrying around a bunch of constraints and have to carry around a bunch of certain types are generic in your constraints. And this is a very powerful tool to work with generic ASTs. In fact, we're using this already with a couple master students, and I myself am also using the library. And if you're curious about how to handle GADTs, drop by tomorrow at Haskell Symposium at 9:30, because I'm going to tell you how to do that with this library, which is this will be in the season 2. Until then, just clone the library, use it, hack it, and let me know what you think. Thank you very much.
3 words. Can you override recursive definitions, quality of type errors, GAC performance, compile time events?
The first one was override?
Yeah, can you override? You basically have now catamorphisms.
Yes.
Are you forced to use that, or can you basically...
Oh no, you can override it. You don't need to use that. The quality of the error messages are as good as a generic programming library is going to be. So it's which is a polite way of saying that they are horrible, but given the context, it's actually acceptable. And the performance is actually quite surprising. So I'm using this to work with ASTs that come from files with more than 1,500 lines, and it works like a charm. So far I didn't run into performance problems.
I was wondering, can you handle maybe regular recursion? So in my recursive case, the type kind of changing in some way. I can do this in regular generics, but I was wondering if this code's approach can handle this.
Yeah, so not really, because we only handle types of kind star. So there's no notion of type parameter. There's a way to handle that. I'm going to be talking about it tomorrow morning. So drop by.
Have you looked at? So you said that you don't carry around constraints. You instead define all the combinators in a recursive way. have you looked at instead defining the combinators as type classes and then do the recursion that way? Because you would get, I think you'd get faster performance because the recursion can be unloaded from that.
I don't know. You can have equations that tell that from after a true is going to be the identity, which helps, but the discharging of the requirements to carry constraints around come from the fact that your whole value is already represented using standard, using in-library combinators and data types. So I don't know, but we can definitely take a look at it later if you're interested.
I wonder why you choose not index the recursive parameters and not any arbitrary index type. Like, for example, you can say, if you have bool, you know that they are just two mutually recursive data types.
Yeah, because these are hard to pattern match on an arbitrary point, and we actually want to have singletons to pattern match on so that we can uncover which recursive type we're talking about. So nuts are just a design choice to make it more easy to use and perhaps a little bit less generic, but still.
You mentioned at some point that there was some restriction regarding polymorphism, so this only works with polymorphic.
Yeah, unfortunately.
I'm not so familiar. Why is that?
Because yeah, so it's if you think about type parameters in a mutually recursive setting, well, every type in the family would have a different number of parameters, and they would. So basically, it is doable. You just have to heavily complicate everything, because then all of the types will have not only a variable number of parameters, but also a context in which they apply at each call site. So you have to carry that around in your generic representation to actually represent the AST. So this makes it very complicated to use. And since most of the times, especially when talking about ASTs, you already know what is the type that you actually the template Haskell generation, it actually carries a beta reduction mechanism inside to actually monomorphize types on the call site and instantiate it to the correct parameters, and then generates the template Haskell stuff because of that.
Actually, I have a quick question. So you mentioned briefly that you could use fin and to sort of keep track of these, but that would be too hard. Did you try it? Did it work? Did it? I mean, or were you working in Agony? You sort of mentioned that it would be hard there too. Just sort of curious.
Yeah. So fin, the first big difference was we would need to bring in typing type, which we don't. So this is one of the reasons for not having fin there. We tried. The code becomes much more complicated though, because then not only your language of atoms receives an extra parameter, which means that everything else receives an extra parameter, but there is well, one more complicated pattern match to perform everywhere. So, yeah. Thank you.
Thanks.
Well, good morning, everybody. It's me again. For those that were not here before, my name is Victor. I'm a PhD student at Utrecht University, and I've done this work as a tangent of my PhD, together with my lab mate Alejandro, who unfortunately couldn't be here. But, well, you might be asking yourself, why do we need yet another generic programming library yet? Because every year somebody comes up and presents one. Well, unfortunately, nobody has yet presented one that has a combinator-based approach for mutually recursive families, which tends to be very useful if you're working with arbitrary ASTs. Moreover, GHC keeps evolving, and every year we are able to do more and more cool stuff, which in turn helps us make better and better libraries. So we set ourselves to design and implement a user-friendly library for generic programming with mutually recursive families. I mean, it's in quotes here because this is as user-friendly as generic programming for mutually recursive families can be. But I think we did strike a good balance there. Now, when you are actually writing these libraries, you do have to ask yourself a couple questions, and you do have to navigate the design space. And I like to see the design space of generic programming as three independent directions. So first you have to decide which class of data types you're going to be representing. Second, you have to decide how you're going to handle recursion. Are you going to represent recursion explicitly or implicitly? And third, you need to decide whether you're going to be using codes or you're going to be using pattern functors, the distinction of which will be cleared soon. These are not right or wrong choices, but these are going to impact how expressive and how easy to use your library is going to be for a bunch of different features. So far, this is the landscape of generic programming, at least type generic programming. You have a couple other libraries like Scraper, Bullet Rate, which use data and typable, and I'm not going to talk about those because those use a different approach altogether. But we do have pattern functors, which had started with regular and then went to multi-rate, and now we all know GHC generics, and generics SOP came to solve the problem for codes, but there's a big blank space here in this column, which is exactly where we fit. And I like to call our library Mr. SOP. Well, nevertheless, let's take a look at this design directions, and let's see which are the drawbacks of each. And by the end of the talk, I hopefully will have shown you how you would naturally arrive at generics Mr. SOP yourself had you laid it out on a paper as well. So for GHC generics, we use pattern functors approach, in which we actually define representation of data types using this fixed binary combinator language, which are these pluses and times here, and this K1 standing for constants. So we would define the generic representation of a binary tree with data on the leaves to be either just the data, so the choice here on the plus indicates the choice of constructor you have, and here you have a product of two binary trees. We would then package it all together in a type class, which would wrap the isomorphism between T and the uniform representation of T, and then you could work over uniform representations, which would allow you to define functions for whole classes of data type without rewriting a single line of code. For those that are not familiar with these operators, which come from GHC generics, and they are defined like this, and you should be using GHC generics because it's awesome and it solves a lot of cool problems. Yet, we should note that GHC generics does not handle recursion. So here, GHC generics is on the pattern functors, no recursion side of things. And we only know that this data type is recursive because we see that the bean constructor here actually appears on the left-hand side, and we actually have to do some fancy type families if we were to figure this out by ourselves. We could fix that, and that's what regular does by introducing the identity functor, and then we could represent binary trees like this instead, and we say, okay, it's either a leaf or two recursive positions, and then we would actually have a explicit list fixed points, and this isomorphism holds. This is really cool because all of a sudden you win the ability to do recursion schemes over your data types, which is a very expressive way of writing functions. Regardless though, when you have pattern functors, you define your generic functionality by the means of class dispatch, which basically means that you are defining your functions by induction on your combinators, which are these guys, and this means that you need to have instances for all of the separate parts, and eventually you can package your definition all together by saying, okay, translate a binary tree into its generic representation, and then apply the generic size function. Now, this is all fun and games, but have a bunch of problems. Namely, you have absolutely no guarantee about the form of the representation. So for instance, products of sums are valid representations, and this restricts, sometimes you actually want to talk about some normal form of types, which is very useful when you're defining especially more complex functionality. Another problem is that you have no guarantee about which combinators are used in the representation. So for instance, maybe is a perfectly valid star-to-star type, which are going to break your class dispatch horribly. So if somebody actually makes a mistake when writing handwritten representations, you have no